Good morning, sir.
Okay, hello everyone. Good morning, all of you. There is always light after dark. Okay, everything goes in cycles. We need not be happy because there is light always. There will not be light always or dark always. Right? We have to be ready for the dark when you are in light, and you can be hoped for light when you are in dark. And this is a great quote by Mary Curie. Nothing in life is to be feared. It is only to be understood. Now is the time to understand more so that we may fear less. And today is the birthday of one great spiritual leader, Mata Amritanandamayi. And she says, be like the honeybee who gathers only nectar wherever it goes. Seek the goodness that is found in everyone. As I tell many times, nobody is full good or nobody is full bad. There is good in everybody. So only thing is, you have to seek the goodness in the other people if you want to be happy with everybody. And also she says, whatever binds us most, whatever is dearest to us, that is what we should offer to the Lord. Doesn't a mother give her child whatever she thinks is the best? So like that, whatever you think is the best, that you have to offer. So when you help somebody also, we have to do like that. So in her public talks and in articles, Amritanandamayi has taken up several social issues, including the importance of selfless service, need for interreligious harmony, for environmental protection, and of desegregating science and spirituality. She also regularly speaks on the importance of women's empowerment and gender equality, as well as that of humankind cultivating what she refers to as Vishwa Matrutvam, that is motherhood, an attitude of motherliness towards all beings in creation, specifically through expressing compassion, patience, and selflessness. Okay, she was doing a lot of social service. Some of the examples I give you here. In India, and Amritanandamayi Mutt provides 10 million free meals to poor people annually via its various centers. Likewise, Embracing the World feed more than 150,000 annually in North America through 49 centers that conduct a program called Mother's Kitchen, started in 1987. And many other countries also it is there. I am not writing all of them. And MUT is also currently deploying filtration system with the goal of providing clean drinking water in 5,000 villages centers throughout India, which would provide water purification to 10 million villages. Since 1998, the MUT has constructed over 47,000 houses for the homeless in 75 locations throughout India. And the MUT manages the 1100-bed super specialty hospital, Amrita Institute of Medical Sciences in Kochi, which is launched in 1998, as well as several other free health centers, clinics, medical dispensaries, hospices in India. In total, the MUT has provided totally free medical care and surgeries to more than 4 million people since 1998. It also started Amrita Shri in 2006. This program has helped more than 200,000 from women from self-help groups throughout India. And the MUT also runs a scholarship program that currently provides 50,000 scholarships for economically challenged children throughout India. And they donated 15 million US dollars to the government of India's Nimami Gang, that is Clean the Ganges program, for the specific purpose of constructing toilets for poor families living along the Ganges River. On 27 of September 2015, Amritanandji pledged that her NGO would dedicate the value of another $15 million to toilet construction and other sanitation efforts, specifically in India's Indian state of Kerala. Okay, so you can see so many things she is doing. Okay, today we will have the lecture 16 on consistency, linearization, and stability. So because last class I'm talking a lot things about the consistency and stability, so we'll see what they are. And in the last class also what we have done is multidimensional parabolic solvers we have discussed. So mainly 2D parabolic solvers, solving with ADI method, that is alternate direction implicit method, and using Planck-Nicolson method, and also using fractional step method. And also we have seen how we can compare ADI and the Planck-Nicolson. We have seen that ADI is nothing but an approximate factorization of Planck-Nicolson method. And we have seen an example problem. And we also have seen how to extend all these three methods, ADI, Planck-Nicolson, and fractional step methods for 3D flows also. Okay, these things we have discussed in the last class. And today we discuss about what is called as consistency analysis. The finite difference equation of a partial differential equation is said to be consistent if the FDE approaches the original PDE as the subsize approaches 0. Okay, we have converted the partial differential equation into finite difference equation, or we have discretized it into algebraic equation, which we call it as finite difference equation FDE. So these two should be same, right? It should be FDE should become a PDE as the step size approaches 0. For delta x, delta t, or delta y, they approach 0, it should become original partial differential equation. So under what conditions this becomes that actually we have told as order of accuracy, delta t, delta x whole square, like that. But I told you in Dufort-Frankel there is one more term comes. Okay, how to find it out? How to find out whether a finite difference equation is consistent or not? Under what condition is consistent? So that thing we will do now. Okay, so example 1, FTCS scheme of parabolic partial differential equation. Okay, this is the original model equation, and we know that this is FTCS, UAN plus 1 minus UAN by delta t, like this. So what we are going to do is, we have to substitute the Taylor series expansions for each of the terms that is present in the finite difference equation, and see under what condition it becomes the PDE. Okay, that's what we are going to do. Okay, I will do this. So we have taken ut is equal to uxx. So uin plus 1 minus uin equal to u into ui plus 1n minus 2uin plus ui minus. Okay, this is the way. Okay, delta t, if I take it to that side, alpha delta t by delta x whole square becomes diffusion number. So this is the way we have the FTCS method. So what we have to do is, here I have uin plus 1, ui plus 1n, and ui minus 1n. I have to see what are the partial, that is Taylor series expansions for that. So what will I do? uin plus 1 is equal to, what will I get? Can anybody tell me? uin plus
delta t del u.
Yeah, delta
Del.
t dou u by dou t, right? I will write ut plus delta t whole square by factorial to utt, right? Second derivative of with respect to time, and delta t whole cube by factorial 3 uttt. Okay, plus etc. That is the left hand side actually. Anyhow, I will write the other things. So if I want to write ui plus 1n, this will become uin plus. Can anybody tell me what is the next term?
Delta
This
x
is
ux.
delta x, right? Because here I am taking I plus 1, the next point in the x direction. So delta x ux plus delta x whole square by factorial 2 uxx plus delta x whole cube by factorial 3 uxxx plus etc. Like this. Similarly, if I take ui minus 1n, in the place of delta x, I have to put minus delta x. So uin minus delta x ux plus delta x whole square by factorial 2 uxx. Here minus delta x whole cube by factorial 3 plus uxxx plus etc. Like this. So these are the only things I have because UIN is okay, no problem. So I have to substitute these three into the finite difference equation. This is the finite difference equation, and this is the partial differential equation. I have to see under what conditions this will become this. Okay, so that's it. Okay, so what I do is I will write it. UIN plus 1 minus UIN when I write. So this UIN gets cancelled on the left hand side. So I will have delta T UT plus delta T whole square by factorial 2 UTT plus delta T whole cube by factorial 3 UTTT plus etc. is equal to D into, okay, in UIN plus 1 there is one UIN, UI minus 1 there is one UIN, here minus 2 UIN. So UIN gets cancelled. Usually in all the things UIN gets cancelled. So UIN gets cancelled. Now I have to take the sum of these two. So when I take the sum of these two, UIN anyhow gone, and delta x UX gets cancelled. Am I right? And 2 times delta x whole square by, so I will actually take 2 outside. Delta x whole square by factorial 2 uxx. Again, odd derivative gets cancelled. I will get delta x whole power 4 by factorial 4 uxxxx plus etc. Like this. Am I clear?
Yes, sir.
So here, what I do is, in the place of d, I will write alpha delta t by delta x whole square. Okay, so I cancel delta t both sides. So what will I get here? Ut plus 1 delta t goes off. So delta t by factorial 2 utt plus delta t whole square by factorial 3 uttt is equal to, on the right hand side, alpha, and one delta x whole 2 will be there. Okay, 2 also I will take inside. Delta x whole square I cancel. So the first term delta x whole square is gone, 2 is gone. So I will get uxx plus, in the second term, one delta x whole square goes off. In the denominator I have 4 into 3 into 2, 2 is cancelled. So 12 will be there, uxxx plus etc. Like this. Okay, so original partial differential equation is ut is equal to ux, alpha uxx, alpha uxx. So here all ut is there, alpha uxx is there. All other terms must be 0 to make this as original partial differential equation. Am I right? So under what conditions? So you can say, you can see from the that if delta t tends to 0 and delta x whole square tends to 0, then this will become finite difference equation is equal to partial differential equation. So the order of accuracy we will say as delta t delta x works like this. Or it is consistent if delta t tends to 0 and delta x whole square tends to 0. Is this okay?
Yes, sir.
Yeah. So normally what we feel is all schemes will become like this only. But that exception, whatever is there due for Frankel, we will try to do that. Okay. So what is due for Frankel scheme? Okay, this we have done it now. Okay, so this is the way we got, if you remember, right? So we have taken central time centrals to CTCS, and UIN, I have replaced it by the average of UIN plus 1 and UIN minus 1. So when you simplify and take UIN plus 1 to the left side and UIN minus 1 to the right side, we got this in this way. Okay. So 1 plus 2d uin plus 1 is equal to 1 minus 2d uin minus 1 plus 2d into ui plus 1 and ui minus 1. 1 minus 2d ui n plus 1 minus, I will bring that also this side, 1 plus 2d into ui n minus 1 is equal to 2d ui plus 1n minus ui minus 1n. Plus or minus? Plus. Plus. Here it is plus. Here 1 plus and 1 minus. Okay, this is 1 plus. Is it right? 1 plus 2d ui n plus 1 minus of 1 minus 2d ui n minus 1 plus 2d into sum of those two. Okay, these things we have taken, and so we will expand this using Taylor series expansion. So we will get 1 plus 2d into uin plus 1 as we have written previously, uin plus delta t ut plus delta t whole square by factorial 2 utt plus delta t whole cube by factorial 3 uttt plus etc. Minus of 1 minus 2d, I will write it as 2d minus 1 into uin minus 1. So I will get alternate plus and minus. Uin minus delta t ut plus delta t whole square by factorial 2 utt minus delta t whole cube by factorial 3 uttt plus etc. This is on the left hand side. And on the right hand side, I will get 2d into uin plus delta x ui ux plus delta x whole square by factorial 2 uxx plus delta x whole cube by factorial 3 uxxx plus uin minus delta x ux plus delta x whole square by factorial 2 uxx minus delta x whole cube by factorial 3 uxx. Like this, very good. So we will try to simplify it now. And on the left hand side, if you see uin, how many uin will be there? One plus 2d plus 2d minus 1. 4d, right? 4d. And how many uin on the right hand side? 2d here and 2d here. Okay, so 4d. So uin gets cancelled on both sides. Okay, then ut, okay, delta t ut, how many will be there? Again, if you add these two, that is 4, it's cancelled, right? No, not cancelled. Okay, delta t here minus delta t. So 1 plus 2d minus 2d plus 1. That is 2 times, right? Am I right?
Yes, sir. Yes, sir.
And here for the next term, I think 4d delta t whole square by factorial 2 utt will be there, right? And here again minus 2 will be there, delta t whole cube by factorial 3 utt plus etc. Like this I will have on the right hand side, the left hand side, and right hand side.
Sir, sir. Plus
Yes,
2. Plus 2.
this is plus 2. Yeah. Same. Thank you. Plus 2. And on the right hand side, this delta x ux gets cancelled, right? This and this gets cancelled. And the next one, 4d it will become 4d delta x whole square by factorial 2 uxx. And delta x whole cube also gets cancelled. I will get 4d delta x whole square by factorial 4 uxxx, etc. Like this. Okay, now we will try to somewhat simplify. Okay, and 2 I can get cancelled throughout. So 2, if I cancel here, 2 cancel here, and okay, this 4 will be as it is, and denominator 2 I will cancel. And I think both 2's will be cancelled, right, with 4. I'm dividing 2, another 2 here, so that 4 gets cancelled. Okay, here 2 is done. On the right hand side, again this 4 will be gone, this 2 and that 2, and 1, 2 will be gone here, like this it will be. Okay, and this D, okay, I will write that substitute D. Okay, here delta T plus D means alpha delta T by delta X whole square into delta T whole square UTT plus delta T whole cube by factorial 3 UTTT plus etc. is equal to alpha delta T by delta X whole square UXX plus 2 alpha delta T by delta X whole square delta X to the power of 4 factorial 4 UXXXX. Like this it will become. So it will become delta T plus, sorry, UT also is there, right? Okay, one delta T I cancel everywhere. This delta T goes off, this delta T goes off, one delta T goes off here, and this delta T goes off, this delta T goes off here. Okay, what is that I am left with? UT plus alpha delta T by delta X whole square UTT plus delta T whole square by factorial 3 UTT2 is equal to this delta X whole square gets cancelled. So alpha UXX plus 1 delta X whole square goes off. So it will become 2, okay, this 1 by 12 it will become 1 by 12 alpha delta X whole square UXXX plus etc. Like this it will become. So if you see this equation, and this is finite difference equation, and partial differential equation is ut is equal to alpha uxx. Okay, this should be there and this should be there. All others should be 0. And if you see, if delta t tends to 0, this will become 0. And the other terms will be delta t whole cube, delta t to the power 4, like that. Similarly, if delta x whole square tends to 0, next time we'll have delta x power 4, next delta x power 6. All those things will be 0. But this additional term is there here. Okay, so this is 0 only when delta t by delta x whole square tends to 0. This is the additional thing will come here. Am I clear? Okay, what is the meaning of that? If delta t tends to 0, delta x whole square tends to 0, then delta t by delta x whole square may tend to 0, like that people may think. But it depends on at what rate it is tending to 0. If delta t is tending to 0 slowly, or and delta x tending to 0 fast, then it will have a finite value. It will have a finite value, delta t by delta x whole square. So what happens is, if delta t by delta x whole square, right, if tends to a finite value, it happens if delta t tends to 0 or delta x tends to 0 faster than delta t. So if denominator becomes faster, smaller one, then the whole delta t by delta x will become some finite value. So if it has finite value, what it becomes is the previous equation. It will have a finite value ut plus some finite value into utt will be. And delta t by delta x, if you take some k, right? So this will become alpha k square utt is equal to alpha uxx. So this will take this form. So what it means is, originally the original equation is ut equal to alpha uxx, which is parabolic. But this is hyperbolic, because this second order term utt is there, which is some finite value. Okay, so this behaves like hyperbolic equation, and I wanted to solve a parabolic equation, but I'm solving a hyperbolic equation. So it becomes like that. Is this thing clear, whatever I'm telling?
Yes, sir. Yes, sir.
Yeah. So this is about whatever yesterday I have given some statements, just I am uh, proving that. Okay, this is done here. This is the additional one I have. Okay, it becomes like this, alpha k square like this, and which represents a hyperbolic equation. Okay, there is another thing called as methods of linearization. So if you remember, we get ut plus ux is equal to alpha ux. If it is 1D, right, on the left hand side, the convection term becomes u dou u by dou x. So this is a nonlinear term. Okay, so as I told, this gives always problem, because I have u dou u by dou x. Suppose if I discretize it like this, so ui j, here ui plus 1j, okay, this u dou u by dou x. If I want to discretize it, so ui, I will take one dimensional so that it will be easier. So ui into, so what is the difference here? So you can write as ui plus 1 minus ui by delta x. If I take this way, because usually we will take forward difference or backward difference, because depending on flow is this way or this way. Central difference normally will not work when I have a convection term dominating. Okay, so I have to take one-sided difference. If I take this way, so it will become ui plus 1 and ui square. So when you write the algebraic equation, there will be square terms will be there, unknown terms. Okay, so I want to find out if it is implicit. So this will become k plus 1, k plus 1, k plus 1. So this is unknown, this is unknown. I have multiplication of the unknown terms, and again ui k plus 1, ui k plus 1, multiplication of unknowns. Okay, so this is like non-linear. So I will not get a linear set of algebraic equations where I can use Gauss-Seidel method, Gauss elimination method, or tridiagonal matrix method like that. All those things will not work. So what should I do about this? So there are various methods are there. So one of the method is called as lagging. Okay. So this is what we are going to do. In this linearization, the coefficient is used at the known value, that is at station I. Okay, if it is space marching, he is doing space marching, I am doing for time marching. And so the finite difference representation becomes uij into ui plus 1j minus uij by delta x. There is one unknown ui plus 1j. Okay, suppose if I want to write it right way, okay, I'm doing the other way as book told. So u do u by j. So I have values at I and to be calculated at I plus 1. So actually I have to write ui plus 1 into ui plus 1 minus ui by delta x like this. Okay, ui plus 1 is the unknown. So here ui plus 1 into ui plus 1 becomes non-linear. Okay, so if I want to make it lagging means what I do is I will take this as ui only. ui into ui plus 1 minus ui by delta x. Here, what is the unknown and what is the known? Only ui plus 1 is the unknown. So ui into ui plus 1 is linear only. And ui square also is a linear because they are known values. Is my point clear or not? I know values at I am calculating values at I plus 1. Okay. Strictly speaking, I have to write this way, which results in nonlinear algebraic equation. Because ui unknown square is there. But here, by lagging, I am getting linear equation. Because in the term ui plus 1, I know ui. Okay, it is a constant. Similarly, second term ui square is there. That is also because known value, that is a constant only it will become. So the whole equation will become a linear equation. Is my point clear or not?
Yes, sir.
Okay. So this is space marching I am telling. So it can be in So in the previous one, I am writing in okay, the time marching like that. So here, what we do is this uik plus 1, I will take it as uik. Okay, k is past iteration, old one, and k plus 1 new iteration, like this. So actually, I have to write like this. So sorry. Yeah. So here I can write this as uik, one time lagging behind. So it will become uik plus 1 minus uik. So if I write like this, because this is known value, uik and uik plus 1 it's okay, and uik square also is okay. So it will become linear, but this will become non-linear. So this is lagging behind. Okay, so one step we are making it lagging behind so that it will become linear. So this is one method. And the other method, another method, iterative.
Sir,
Okay, so here
sir, can you repeat
yes.
why we do not use central method, central difference?
No, okay, that we will do when you are doing hyperbolic. Okay, so what I do is suppose the flow is dominatingly going in this direction. If it is going this direction, so the properties at this point will not depend on the point after that, isn't it? Because it is coming this way. So it depends on the property ahead of it. Upstream value only. It will not depend on the downstream value. If I use that, actually it becomes unstable.
Okay, sir.
Is it clear or not?
Yes, sir. Yes.
Okay. So it is like always you are going to the class in one direction only. So the next room fellow only you will see. The room, the fellow behind you, you will not see. Something like that. Okay. So one side
Yes, sir.
fellow only will be influenced. Okay. So the iterative method, what we do is, So again, we take this way, ui plus 1j, ui plus 1j plus 1, and like this. Okay. So in the first iteration, k equal to 1, ui plus 1j is the value of the previous station. That is uij. Once ui plus 1j k plus 1 has been computed, the coefficient ui plus 1j k is updated, and a new solution is sought. The procedure continues until the convergence criterion is met. So at ui plus 1, so here what we do is, here it is something like lagging only, but we will do iteration. So what we do is, here I am using the old value, and here I am using the new value, and I am calculating. I update the ui plus 1j. Okay, at k plus 1 I will calculate, and that new value I will substitute here. Here I old value. So in that way, these two values, so what we do is ui plus 1j k plus 1, it is new iteration, and minus old iteration, it should be less than or equal to epsilon. Like that, I have to iteratively do it.
Sir,
Yes.
hello.
Yes.
Sir, can you please repeat this again? Like which value we are updating, sir, in this method?
Yeah, here ui plus 1j I update. ui plus 1j k is there. Here ui plus 1j k plus 1 is there. But previously also I am doing, this is something like lagging only. Is it clear? This is n plus 1 time step. This is nth time. Okay. So using this, I calculate this, and that new value I substitute here, and again I recalculate this.
Okay, sir.
So like that I will do iterative method. This is one method. And there is another method, a bit popular one, which we will use a bit later. Okay, this is called as Newton's iterative linearization, AB. Okay, so it is like I have two dependent variables. One can be u, it can be v, or one can be u, one can be dou u by dou x, like that. Okay, so a k plus 1, b k plus 1. Like this, I have two unknown terms multiplying each other. Okay, so where a k plus 1 is a k plus delta a. Okay, old iteration value, and if you add something, you will get new iteration value, something like that. Similarly, bk plus 1 is equal to bk plus delta b. Okay, so I will write this as ak plus delta a into bk plus bk plus delta b. And so it will become ak bk plus delta a bk plus delta b ak. And here it is like this. Okay, this, and okay, one more delta a into delta b also you get. And here and ak bk plus delta a means ak plus 1 minus ak into bk plus delta p means bk plus 1 minus bk into delta b, sorry, ak plus delta a delta b. Because these two are small, I neglect this. Okay, and if I see here, ak bk is there, Here minus AKBK is there, gets cancelled. Here one more AKBK is there. Okay. So out of 3, only 1 will be there. So I will write it as AK plus 1 BK plus BK plus 1 AK minus AK BK. Okay. One positive AKBK is there, 2 negative AKBKs is there. One AKBK gets cancelled, one negative AKBK remains. Okay, this is the thing. This is AK plus 1, BK plus 1. Okay, can you see what is the difference now? I say this is linear. Am I right?
Yes, sir.
Yes, sir.
Because K plus 1 terms only are not known. AK plus 1 is not known, into BK is a constant. Here BK plus 1 is known, into AK is constant, and this is a constant. So it becomes linear. Okay, this is the way we write. This is the only thing is, well, how can we get this? Because this is the small, we are neglecting, which assuming it to be small term. Because of this, I am getting it linearized. Okay, this formula we have to remember. So AK plus 1 BK plus 1 is equal to AK plus 1 BK plus BK plus 1 AK minus AK BK. So now it can be U dou U by dou X term is there. So this K plus 1, this K plus 1 if I have, right? So UK plus 1 dou U by dou X at K, right? Like that we will write. Okay, it is like U K plus 1. So dou U by dou X, maybe UI plus 1 minus UI by delta X. These two will be at K plus BK plus 1, that is dou U by dou X or UI plus 1 minus UI by delta X. This is at K plus 1 into UK minus UK and dou U by dou X K, that is UI plus 1 minus UI by delta X. These will be at K. Like this, I have to expand it. So only thing, it will become a bit larger, but which cannot be handled can be handled. Maybe I have a bit more burden, but it doesn't matter. So you can see something like this. Okay, this is the way it will become. And if I apply it like U dou U by dou X like this, okay. So this is Uij means this is at K, which is known. Okay. So dou Ui plus 1 J K, du I plus 1 minus Uij. So this is K plus 1. This is like known value. Okay. Like that. Okay. This is the way you will get something. Okay. So this you can go through. That is the way we simplify it. Now we will talk about stability. So when you go for stability, we will see stability is because some error is increasing too much. Okay. So it is diverging, something like that. So what are the sources of error? So one is discretization error. Or truncation error. Okay. So where do we get it? Because what we are doing is we are writing every term in finite difference expression. So we are higher order terms we are neglecting. Okay. So the higher order terms in the Taylor series expansion so represents the truncation error or discretization error. Okay, so this is from formulation only. Okay, so formulation itself results in some discretization error or truncation error. And to reduce that, sometimes we are making it higher order accuracy, second order accuracy, or third order accuracy, like that. Okay, so that is the only thing we can do. But still, I have discretization error present with any scheme. Okay, and the second is, as I told, round off error. So discretization error, I can increase, decrease something. It depends on the formulation, and it depends on me. Okay, and but what round off error is due to?
Computer.
Yeah, the precision of computer. You will say single precision, double precision, okay, long double, like that. Okay, so but still you cannot avoid it. There is round off error present with any computer, right? So the round off error is due to the precision of the computer. So these are the errors. So we have to mainly focus on round off error. So what happens if there is round off error at a particular point, at a particular iteration, and how it is going to affect the neighboring points in the first iteration, and the next iteration, how it is going to spread. Okay, this error is going to spread to the neighboring points. As we have seen boundary condition, what happens? It goes to the next grid point, grid point, like that, iteration by iteration, it spreads into the domain. In the same way, as the information goes from boundaries to interior, in the same way, the error also propagates. So that is error propagation. Okay, so I have to see how the error propagated. As the error propagate, right, whether error increase or error decrease. If error increases, no problem, convergence. If error decrease, no problem, this is convergence. And if error increase, then it will diverge. Then it will become unstable. And this becomes stable. So this is what we have to check for each type of thing. Suppose if you take epsilon ij is the epsilon, okay, one dimensional, if I take epsilon I only. Epsilon I n is error at point I at nth iteration. Okay, this is like this. At the same point, when I do in the next iteration, this is epsilon I n plus 1, error at point I at n plus 1th iteration. In the next iteration, what is happening to the error? So if I see here, epsilon I n plus 1 by epsilon I n, okay, so modulus. So what should it be?
If less than 1, then convergence.
Yeah, it should be less than or equal to 1 for stability or convergence. If it is greater than or equal to 1, so at the same point, the error is increasing like that, so it will diverge. So this is the condition for stability. Okay, so here, if you see, okay, this is, there are two methods. There are two methods. One is discrete perturbation stability analysis, and another von Neumann stability analysis. Okay, these two are the methods. Okay, in the textbook, both are explained, but actually this is not much used, but it gives some physical idea, right? You can go through that example, how it propagates into the next point, like that. physically you can feel it. Okay, but we are not doing that. We are going to do this. This is most popular and easy to apply. Okay, in a very short way. Okay, simple way. This is called as von Neumann stability analysis. This is what we are going to concentrate. And so here you take A as the analytical solution of the partial differential equation, means exact solution. And D is the exact solution of difference equation. Okay, that is no round of error. There is only truncation error. The difference between A and D is the truncation error. Am I clear? Or discretization error. So that's what discretization error A minus D. This is the solution of the partial differential equation, which is the exact solution of the original partial differential equation. And D is the solution of the finite difference equation. Okay, what is the difference between partial differential equation and finite difference equation? Only discretization. So that is the error. Discretization error is A minus D. But when you are solving numerically using the computer, so I am getting a solution. That is numerical solution from a real computer with finite accuracy. So the difference between D and N will be round of error. N minus D is the round of error epsilon. So N is equal to D plus epsilon. Okay. Now you have the equation. Suppose I am taking FTCS method. TAN plus 1 minus TAN by delta T is equal to alpha TAN plus 1, like this. Okay. And here T is nothing but numerical solution. I am going to get numerical solution. And we know that from the previous slide, N is equal to D plus epsilon. I substitute D plus epsilon there. So everywhere for TAN plus 1, I write DAN plus 1 plus epsilon IN plus 1. For TAN, DAN minus epsilon IN. Like that, I substitute D plus epsilon for all the terms. And D is the exact solution. So D must satisfy this equation. This equation, if I put D there, it should satisfy the equation. And if I subtract this from this, I'm going to get epsilon IN plus 1 minus epsilon by delta T, like this. Means epsilon also satisfies this equation. N satisfies this equation and D satisfies this equation. So epsilon also must satisfy this equation. So that is what it is taken here. Okay, and I know that epsilon I by N plus 1 by epsilon I should be less than or equal to 1 is the condition of stability. Okay, so now I have to see. So what is this epsilon I? So von Neumann has given an expression, right? An empirical expression for the epsilon IN. Okay, so this is the way. He has given. Okay, so N is equal to D plus epsilon. So N is numerical solution and D is the solution of finite difference equation. That is, this is exact solution of finite difference equation. And epsilon is round off. Okay, so a given finite difference equation N should satisfy, D should satisfy, therefore epsilon should satisfy. Okay, this is the one I have to take. Okay, and this epsilon is given to be a particular form, right? This is like e power a delta t and e power I kn, sorry, e power a t. E power I kn. This is epsilon I. So that is what he says is the error vary exponentially in time and Fourier way, I can write like this, in space, that is oscillates also. Okay, so this is the way it is assumed. So he has given this expression. Okay, if epsilon in is equal to e power at e power I kmx, where km is wave number, we call it as wave number, and a is the amplitude of error. Okay, if I want to have epsilon in plus 1, so what will be the expression? This is after time delta t, right? So at time t, that wherever t is there, I have to write t plus delta t. It will become e power a into t plus delta t, e power I kmx. So if it is like this, so what happens to epsilon in plus 1 by epsilon in? This is also called as amplification factor. So many times it is given a symbol G. So what will it become? G is equal to this by this, e power a into t plus delta t, e power I kmx by e power at, e power I kmx. So this goes off, and this will become e power
A delta t.
a delta t.
A delta t.
This is the amplification factor. So condition for stability is mod g should be less than or equal to 1. Means mod e power delta t should be less than or equal to 1. This is the condition for stability. Okay, this I have to see under what condition this will be satisfied. Okay, if I do the application for FTCS scheme, okay, where I have got okay, I will write this as tin plus 1 minus tin is equal to alpha delta t by delta x square is d, ti plus 1n minus 2 tin minus ti minus. So now what I have to do is, because epsilon satisfies this, replace t by epsilon. So epsilon in plus 1 minus epsilon in is equal to d epsilon I plus 1n minus 2 epsilon in plus epsilon I minus 1n. Like this. Okay, we have known epsilon in is equal to e power at, e power I kmx. Epsilon I n plus 1 is equal to e power a into t plus delta t into e power I kmx. And you tell me what is epsilon I plus 1n? So I want to get the
e to the
error.
power 80.
x plus delta x point I have to want e power at. It is same because superscript is n only, and here I plus 1 is there. So e power I km x plus delta x. Similarly, epsilon I plus I minus 1n is equal to e power at e power I km into x minus delta x. Okay, this is the way I get. I have to substitute them there. And after substituting, what I do is I divide this whole equation, by epsilon in. Okay, what I am going to get? In epsilon in plus 1 by epsilon in, so if I divide this equation by this, what I am going to get, previously I have shown, I am going to get, okay, I will write here, epsilon in plus 1 by epsilon in is equal to e power a delta t, we have seen it. And if I want epsilon I plus 1 n by epsilon in, what I am going to get? E power at goes of
e to the power of I km delta
e power I km delta x. Similarly, epsilon I minus 1 n by epsilon in is equal to e power minus I km delta x. Okay, this is the way I am going to get. Now, what I will get is okay, divide by epsilon in. I'm going to get e power a delta t minus 1 is equal to d e power I km delta x minus 2 only plus e power minus I km delta x. Okay, so this is the way directly I can write. And so I am interested in e power a delta t. So e power a delta t is equal to 1. I will take to that side plus d times. Okay, for simplicity, I will write km delta x as theta. So that I will get e power I theta minus 2 plus e power minus I theta. So what is e power I theta plus e power minus I theta?
2 cos theta.
2 cos theta. So 1 plus b into 2 cos theta minus 2. So I will take 2 outside. So 1 plus 2d into cos theta minus 1. And if it is 1 minus cos theta, I can write it as 2 sine square theta by 2, right? So I will write like that, 1 minus 2d into 1 minus cos theta. So what will it become? 1 plus 1 minus cos theta is, sorry, not minus only. 1 minus 2d into, what is 1 minus cos theta? Do you remember?
2 sine square theta by
2 sine square theta by 2. It is 1 plus cos theta, 2 cos square theta by 2. So it is 1 minus 4d sine square theta by 2. Okay, this is e power a delta t. This is g. Now what I have to do is mod of this. I have to show whether it is less than or equal to 1 or not. So I have two conditions. 1 minus 4d sine square theta by 2 should be less than or equal to 1, or minus of 1 minus 4d sine square theta by 2 should be less than or equal to 1. Am I right? So in the first one, if I cancel 1 here, and 4d sine square theta by 2 should be greater than or equal to 0. Right? So if you see, what is d? D is alpha delta t by delta x whole square. Everything positive only. Greater than 0, positive. Sine square theta by 2 also is a positive one. So this is always true. no problem. Okay, this is always true, and so this is right, this satisfied. But the second one, if you see here, what I will do is it will become 4d sine square theta by 2 minus 1 less than or equal to 1. If I take 2 this side, it will become less than or equal to 2. Okay, and the 2 gets cancelled like this. So 2d sine square theta by 2 should be less than or equal to 1. Or d sine square theta by 2 should be less than or equal to half. Okay, so this sine square theta by 2, it is always less than 1. So if d is less than or equal to half, this is satisfied. If d less than or equal to half, right? So is the condition. Sorry, half is the condition for stability. Is this clear? This is what we are telling many times. D less than or equal to 1, half is the condition for stability. Is this everything clear?
Yes, sir.
Okay. So if this is clear, your homework for tomorrow is try to do for one. Okay. Check the stability for implicit method. Okay, implicit you can take BTCS. So what should you get? You have to get that it is unconditionally stable. Means you have to show that it is always less than or equal to 1. And you check for Richardson method. Okay, so what should you get? You have to get it is unconditionally unstable. Means you should get always, or it is not never less than or equal to 1. It is always greater than 1. It is always greater than 1. You have to show. It is always less than or equal to 1. You have to. Okay, you will get mod e power a delta t always greater than 1. Okay, so these two you try to prove it. Okay, so I think we will stop here. Any questions? Any questions? So if no questions, we will go for the story. Okay, it's a nice story. There was a poor Scottish farmer, and one day, while trying to make a living for his family, normally he goes to near forest and he will be taking the firewood and all. And at the time, he heard a cry for help coming from a nearby bog. Bog means it's like muddy thing where you get drowned. In movies, you will see, right? So you'll get drowned into that. So he dropped his tools and ran to the bog because new people will not know that there is a bog there, and he knows it. He understood that there was somebody getting drowned and immediately ran there. And there, married to his waist, up to waist, he was drowned into that in black muck, was a terrified boy screaming and struggling to free himself. And then immediately the farmer saved the lad from what could have been a slow and terrifying death. If he didn't save him, he would have died there. And the next day, a fancy carriage pulled up to the Scottishman's sparse surroundings. So a big carriage, a big car or something like that, came to his hut. An elegantly dressed nobleman stepped out and introduced himself as the father of the boy the farmer had saved. So he told, "You have saved yesterday, my boy, and I am the father of that person." And he said, "I want to repay you," said the nobleman. "You saved my son's life." Then the farmer said, no, I can't accept payment for what I did. Because he told, I would have saved that fellow, whoever he is. Whether he is a poor fellow or rich fellow is not the matter. The Scottish farmer replied, waving off the offer. He told, I don't take any money for that. And at that moment, the farmer's own son came to the door of the family hovel. At that time, the nobleman has seen another kid of the same age is roaming around. And he asked, is that your son? The nobleman asked. Yes, the farmer replied proudly. Then I will make you a deal. Let me provide him what the level of education my own son will enjoy. If your son is anything like his father, he will definitely grow to be a man we both will be proud of. Okay, so when the offer is given to the son, he cannot say no because he cannot say no to the offer given to his son. Okay, so opportunity given to his son, and then the nobleman has done that. He has sponsored that farmer's son, and the farmer's son attended the very best schools and in time graduated from St. Mary's Hospital Medical School in London and went on to become known throughout the world as the noted Sir Alexander Fleming, the discoverer of penicillin. Okay, that boy became the famous Dr. Alexander Fleming. And years afterward, the same nobleman's son who was saved from the bog was stricken with pneumonia. And what saved his life this time? Penicillin. Again, his own medicine has saved that person's life. And the name of the nobleman is Lord Randolph Churchill. And his son's name, Sir Winston Churchill, okay, the Prime Minister of London. Okay, someone once said, that's why what goes around comes around. You offer help, and some or other way you are going to get help at some other time. Okay, so what goes around comes around. Okay, this is the great story, and so some quotes of Alexander Fleming. You do not know what you will find. You may set out to find one thing and end up by discovering something entirely different. So many times research goes that way. You are trying to find out something, but some other new discovery will happen. So you can see even for Alexander Fleming also same thing happened. He thought actually the experiment has failed, but that came as the discovery of penicillin. And for the birth of something new, there has to be a happening. Newton saw an apple fall and he found out the gravity. James Watt watched a kettle boil and he invented the steam engine. And Ranjan fogged some photographic plates and he got X-rays. And these people knew enough to translate ordinary happenings into something new. Okay, so that's it. Thank you. Thank you all. See you.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you, sir.
Thank you.